It's, I know it's somewhat a challenge for you to get everything taken care of and put in, but when we get a bunch coming back at me, that's sometimes a challenge to me also, because there's just so many, the volume is too great. I'll just take a look again. All right, as I talked about, we'll be dealing with derivatives up until probably the end of January, and maybe into February, we'll be dealing with the idea of derivatives and applications of derivatives. We learned the quotient rule, product rule, we learned the exponent rule. We now will start dealing with, we have the chain rule we have to worry about. That's the last of the major rules of taking derivatives, but we also just have trigonometric and logarithmic ideas, the early transcendental functions that we have to take a look at the derivatives of. We've already dealt with the derivative of e to the x. And if you remember back, the derivative of e to the x, it was what? Ozzy? Remember? No. Derivative of e to the x? E to the x. E to the x. And what we had to utilize is we had to utilize the limit as h is approaching 0 of f of x plus h. So we had, let's see, e to the x plus h minus e to the x all over h. And we had to break apart e to the x plus h into e to the x times e to the h minus e to the x all over h. Factored out that e to the x. So we're left with e to the h minus 1 over h. And as h approaches 0, this approaches the value 1. So we are left with e to the x as my derivative. Now, dealing with the trigonometric functions, we have to deal with the same rule of limits and derivatives. If I have the limit of sine of x, we have the limit h approaches 0 of sine of x plus h minus sine of x all over h. We have to still utilize the same property in principle. Because if I went t is approaching x, I'd have the sine of t minus sine of x over t minus x. I guess I could use my sums and product rules. I never thought of that. I could use my sums and product rules to be able to solve that. But this is a little bit easier to deal with. Because all I have to remember now is the limit as h approaches 0 of how to expand out sine of x plus h. Using our trig identities. We had an angle addition formula. Sine of a plus b is equal to sine of a cosine of b plus the cosine of a sine of b. Well, we have now x and h in there. That was one of those trigonometric identities that we use and apply. So we have the sine of x times the cosine of h plus the cosine of x times the sine of h minus the sine of x, and this is all over h. I should have left myself a little more room. That's okay. Now, if we would pair up my sine x here, we have the limit as h approaches 0 of sine x times the cosine of h minus sine of x, and this is plus cosine x sine h, and this is all over h. Separating these into two fractions. That would be this fraction over a, or this over h plus this over h. And I'm going to factor out a sine of x here also. We're left with the limit as h approaches 0 of the sine of x times cosine of h minus 1 all over h, plus the limit as h approaches 0 of cosine of x sine of h all over h. All I've done is I just separated them into two fractions being added together. The sine of x and the cosine of x have nothing to do with h. Both of these deal with as h is approaching 0. So those are the only things I worry about in regards to taking limits. So the sine of x can come out front, and the cosine of x can come out up front. So we have the sine of x times the limit as h approaches 0 of cosine of h minus 1 over h plus this cosine of x times the limit as h approaches 0 of sine h over h. I'm now intrigued by that sums and products thing. Now let's type into our function, into our calculator. Y1 is the cosine of h, quantity cosine of h minus 1 divided by h and see what happens as you approach 0. As h gets closer to 0, what happens to cosine of h minus 1 over h? Type in 0.1, 0.01, 0.0001, find your values. It would still take us into angle addition stuff, so no way of making life a little bit easier on ourselves. As h gets close to 0, what happens to cosine h minus 1 over h? What's it get closer to? Adam?
Infinity. Infinity.
Gets closer to infinity? You sure? Anybody get different?
I'm getting 0.
Getting closer to 0?
Yeah.
That's what should happen. This should approach a value of 0. So we're left with sine x times 0. What happens when you have, Make sure you're in a radian mode. Make sure you're in a radian mode also, that might help out. We're in trig. Make sure you're in the radian mode. Now you should get a graph also. It looks like it goes down, it bellows out, bellies out at the origin. My bad. Okay, what happens with the sine of h over h as you get closer to 0? We get closer to Bailey. We get closer to 1. So this is cosine of x times 1. Well, I got sine of x times 0, which cancels out to 0. Cosine of x times 1, which is just cosine of x. So you take the derivative of sine, you get cosine of x. The derivative of sine is the cosine of x. Likewise, we can do the same with the cosine. Limit as h approaches 0 of cosine of x plus h minus the cosine of x all over h. I know we have at the tip of our tongues the cosine of a plus b, cosine a cosine b minus sine a sine b. I know you can rattle that right off. Pythagoras would be really proud of you. So we have cosine x cosine h minus sine x times the sine of h minus cosine of x all over h. And once again, we can group these together, factor out your cosine of x, grouping these two together and factoring out your cosine of x. We're left with the limit as h approaches 0 of cosine of x, cosine h minus 1 over h, minus the limit as h approaches 0 of sine x times the sine of h all over h. And once again, we can go cosine of h minus 1 over h, and then the sine of h over h. And what will happen is this will turn into cosine of x times 0 minus the sine of x times 1. This value here will go to 0. This value here will go to 1. So we're left with a negative of sine of x. So you take the derivative of cosine, you get negative sine of x. Derivative of sine is cosine, derivative of cosine is negative sine. Well, if we take a look at the tangent, we could, if we wanted to, run through limits, which is like, or we can think back to another fond memory of trig class. How can we rewrite tangent in terms of sine and cosine?
Sine over cosine?
Sine over cosine. Which now turns us into a product rule. Or I'm sorry, quotient rule. Because we have the sine of x divided by the cosine of x, which is the quotient rule. So we take the derivative of the top times the bottom. Well, what is the derivative of sine? Well, we just said derivative of sine is cosine. So we have the cosine of x times the bottom, which is cosine of x, minus the top, sine of x, times the derivative of cosine, which is another negative sine of x. And this is all over the bottom squared. All we're doing is we're applying our quotient rule. Well, if I have cosine x times cosine x, this gives me cosine squared x. And negative sine times a negative sine gives me a plus sine squared of x over cosine squared of x. Thinking back to another fond memory of trig class. Sine squared plus cosine squared is equal to what? Sine squared plus cosine squared is equal to the very fundamental first off trig identity that we wrote down. Sine squared plus cosine squared is equal to, oh, how soon we forget. Plug your ears, Pythagoras. Plug your ears. I feel so deflated now. Sine squared plus cosine squared is equal to 1. So we have 1 over a cosine squared of x. Using our trig identities, our trig reciprocal functions, 1 over cosine squared is equal to what? What's the reciprocal of cosine?
Cosecant.
Not cosecant. Secant. So the derivative of tangent is secant squared. Well, how else can we write secant? 1 over cosine of x. Use your quotient rule. Take the derivative of 1 times the bottom, minus the top, which is 1 times the derivative of cosine. So what we're left with on top is a positive sine of x, because this will go to a value of 0. So we have negative 1 times negative sine of x, that gives us positive sine x. And cosine squared is cosine cosine. Well, if I break this apart, I can rewrite this as one over cosine of x times sine x over cosine of x. Just breaking apart. 1 over cosine is secant. And this is tangent. So we're dealing with secant. The derivative of secant is secant tangent. Secant of x times the tangent of x. Cotangent is reciprocal of tangent. So we have cosine x over sine of x. So once again, we can use our quotient rule, derivative of the top times the bottom. Negative sine of x times the sine of x minus the top, which is cosine of x, times the derivative of the bottom, which is cosine of x. This is over sine squared. Factoring a -1 out of both the terms on top, we are left with -1 times sine squared of x plus cosine squared of x, and this is over sine squared of x. And once again, sine squared plus cosine squared will give us back to 1. So we're left with -1 over sine squared of x, which is negative cosecant squared of x. So we're talking about the cotangent. The derivative of a cotangent is negative cosecant squared. And the last one, the cosecant one, is going to fall in line with what we did with the secant one. The derivative will turn into negative cosecant x times the cotangent of x. So your early trains and dental functions, your trigonometric functions, we now have derivatives for these. I would put them to memory, and we'll do enough of them. The derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent, secant squared, derivative of cotangent, negative cotangent, or cosecant squared, derivative of secant, secant tangent, derivative of cosecant is negative cosecant cotangent. So now I want to take the derivative of e to the x times the sine of x. Well, I have two things being multiplied together, so I have to utilize my product rule. So go ahead, find your derivative. Derivative of the first times the second plus the first times the derivative of the second. And what do you come down to?
You get e to the x times cosine x plus sine x times e of the x.
Okay, we had a derivative of the first times the second. Well, you went derivative of the first. You went,
I do backwards.
you did it back. I mean, in my mind, you did it backwards, but, cause I always go derivative of the first times the second plus the first times the derivative of the second. What you did is the first times the derivative of the second plus the derivative of the first times the second. So you did it backwards, which is fine. This is correct. Also, you can derivative of the first is e to the x times the second sine of x plus the first, which is e to the x times the derivative of the second, which is cosine of x. It's the exact same thing, but I just, how my brain works is I'm programmed this way. This is fine for solution. Some books will actually, some books, if you check is for a solution in the back of the book, they will simplify this even further. They'll factor out an e to the x. And they'll write it like this. I'm fine with this right here. But if you want to go the extent a little bit further, that's fine too. We have e to the x divided by cosine of x. We have two things being divided. Go ahead and take your derivative. You have a quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Nathan, what it come down to?
I have e to the x times the quantity of cosine of x plus sine of x over cosine of x squared.
So he went e to the x and quantity of what?
Cosine of x plus sine of x.
Okay, and if you factored that out, it's fine. If you just leave it in an unfactored form, we have derivative of the top, e to the x times the cosine of x, which is the bottom, minus the top, which is e to the x, times the derivative of the bottom, negative sine of x, and this is over bottom squared. These negatives will cancel out to give us e to the x cosine of x plus e to the x sine of x over cosine of x. Once again, I would accept either or. I accept either or. Dealing with trig functions, it's something that you just, once again, as we go through this, you'll continue to utilize and learn the derivative of sines, cosine, derivative of cosine is negative sine. Derivative of secant is secant times tangent. Derivative of cotangent or tangent is secant squared. These are all things that as we continue to utilize them, you'll become more familiar with. Your homework is on page 196, 1 to 23, the weird ones. You're just basically using, it's a lot of product and quotient rule that deals with your trig functions. What I will ask you to do on a test, what will be asked of you on a test is I will give you either the tangent or the cotangent. I might give you a secant or cosecant. I will ask you to prove one of those by using limits and definitions. I will ask you to prove one of those, which is basically using your limit and your, not using limits, using your product and your quotient rule. to prove the tangent or the cotangent, the secant or cosecant. You don't have to use limits, but you'll have to use your product and quotient rule for them. Tomorrow we'll come in, we'll start working with what's called the chain rule. That's when we really start to get into a lot of, heavy lifting with our derivatives. Heavy lifting. Questions? Once again, page 196, 1 to 23, the odds. Do your homework.